All right. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to just guide our steps today. Help us to glorify you in what we do. And again, we just thank you for your many blessings, Lord. In your name I pray, Lord Jesus. Amen. So do you guys have any... well, I already... This was a hint about problem 8. I think everybody here heard what I said. I said take the dot product with A and take the dot product with B of the equation that you want, because it'll give you nice equations for C1 and C2. Alternatively, of course, you can just slog through the algebra and solve systems of equations to find C1 and C2. And that can be done, but it is far easier and more efficient and faster to just take dot products with A and B. That's the, if you will, the secret sauce of that problem. That's really what I'm trying to get you to discover, or hopefully appreciate after you've done the algebra and go back and look at what taking dot products would have done for you. Now, admittedly, that's kind of, it's a slightly unfriendly problem, because in the problem I don't say, take the dot product, right? I forget if I have a large hint in that problem or not. Keep in mind, I did write this problem about 8 or 9 years ago when I was much meaner. Anyway, I guess that's a joke. Is it a joke if no one laughs? I don't know. Okay, so I think there's all kinds of jokes in the world people aren't laughing at, right? One need only look at the U.S. government. Let's see here. Or the Department of Justice, or, well, you go down the list. All right. So do you guys have any questions before I go on here? All right. Well, I need to fire up the projector here, I think. So, when we're talking about, we can talk about a curve or a surface, right? Curves, surfaces. All right. So I don't have much to say about curves today, but basically if you have R of t equals to, well, let me just focus on what we've talked about so far. R of t equals R naught plus, let's say, t times v naught. This is what? Parametrization of line, right, in 3 dimensions. And on the other hand, a surface, what would a parametrization of a surface look like? Well, you might have R of t, well, let's say R of s comma t equal to, say, R0 plus s times a vector plus t times b vector, right? So my point to you here is that the curve essentially is what? It's one-dimensional. If you pick a particular, basically, you can think of t as in some sense being a coordinate along the line. You give me t, I give you where the point is on the line, right? Now, t is only a coordinate for the line. T does not exist as a concept for all of 3 dimensions, right? It is native to the line. A surface like this, we could draw a picture. Something like this, perhaps. And here's a picture of an abstract surface in 3 dimensions, if you will. And what's the deal? Well, if you look at, for example, let's say R1 of s comma 0, what's that equal to? R1 of s comma 0 would be like R0 plus SA, right? if this is R0, the base point, if you will, of the parameterization, then what is this right here? What is this? This is the equation of a line, right? That's the equation of a line which is parameterized by S. And what it's doing is it's starting at R0, and then it's doing scalar multiples of S in some direction, whatever that direction is. Let's, for the sake of the picture, let's just suppose, you know, A looks like this, all right? And so what you got here is like this line, right? This is some point on here would be like R1 of S comma 0. Right? And then, of course, I'm imagining that there's another vector B, which is also, by the way, what we say tangent to the plane. Maybe it's like this, right? Maybe that's B. All right? So if that's B, then this point right here would be what? That point right there would be like R0 plus B. See it? R0 plus B. And the line, if we were to look at it like this would be something like R, let's say R2 of S comma 1. Right? As we put t equal to 1, we're always adding one copy of B, and as we add multiples of A, we go that way, up and down. So anyway, really, what the first blue line is the t equals to 0 line, right? This is t equals to 0. This guy is t equals to 1, right? And we can go over this same story if we go in the other direction. See, we can go like this. This would be like the s equals to 0 line. And if we went up here, this line on the surface would be the s equals 1 line. Because like a parameterization of this dotted line right here would be given by, let's say, R3 of s equals to 1, and then t is allowed to vary. Oh man, come on. So my point to you is simply that you can think of the parameters for a surface as sort of being the coordinates of the surface that are native to the surface. So since the surface is two-dimensional, we need two parameters, which again, they're essentially coordinates for the surface. Now, both of these the parametric view, all right? If we take the other view, the viewpoint of equations, that's trickier, right? Well, we discovered last time, as an equation, we can write this as what? ax plus by plus cz equals to d, right? That's how to capture a plane as the solution set of a what? An equation, right? One equation gives us a two-dimension thing. It subtracts, right? In 3 dimensions, if you have one equation, it leaves you 2 free parameters, which corresponds to a two-dimensional thing, a surface, all right? How about a line? What would the equation of a line be? All right?
Ax plus by equals.
Oh, okay. So, yeah, let's give some details. How about v naught is equal to, let's say, ABC, and let's say r naught is equal to x naught, y naught, z naught. All right? Well, it turns out that you can write equations. They're this: x minus x naught over a equals to y minus y naught over b equals to z minus z naught over c. These are the so-called symmetric equations for a line. I almost never use these things. So what's the idea? How do you fix a line in 3 dimensions? How many equations do you need? How many equations is this? Some people say 2, some people say 3. Independently speaking, it's 2 equations. You could rewrite this as 2 independent equations, but you're right, you could see 3 here. But the third is really given by the first 2, whichever the first 2 are that you pick. consider this. If I'm looking at the line, let me illustrate it via marker. If I'm looking at the line that is formed by the locus of all these markers, right, in 3 dimensions, like so, how do I see this as coming from 2 equations, linear equations like this? Very simple. Oh yeah, go.
It's the intersection of 2 planes.
Intersection of 2 planes, right? So to make that interesting, imagine the line's still here, right? Here's 2 planes, right? Those 2 planes intersect at the spine of the binder. That's where the line is. Are those planes unique? No, they're not. There's infinitely many different choices of those 2 planes that will all intersect along that one line, right? So this is really annoying way of looking at a line in my view. And also it's very, very limited, because what if A or B or C are 0? That can happen, right? And in that case, you can't use the symmetric equations for a line, right? Something simple like x equals to 3 is a plane, right? What's the x equals to 3 plane? X equals to 3 is basically just this. It's this plane at 3, right? It's a vertical plane. It goes on and on and on. What are the coordinates? You could use y and z as parameters for that plane if you wanted to, all right? Listen, I don't expect you to understand everything there is to understand about parametrizing surfaces today. It's something we're going to be struggling with for weeks in this course, all right? So I'm just opening the door to a new world of annoying things you need to remember. Yes? So let me show you some of those in my notes. So it's time for show and tell here. At the end of chapter 1, I have oodles and oodles of, oh, come on. All right, so essentially we have talked pretty much about everything up to page 41, give or take. So I'm pretty much just, you guys can take notes right now if you want, but if you just want to follow along, that's also fine. Because I'll probably be going too fast for you to really write everything down that we're doing. I just want to talk to you about what's said here. All right, so like, if I can, any questions about coming to terms with the lighting in here? There we go. I seem to have forgotten my laser. Oh man. All right, well I'll have to use, I have other means, it's okay. This will do. So, equations of intersecting planes. Basically in here, you don't have to read this super carefully. All I'm doing in here, I'll explain it to you, is I'm taking a pair of arbitrary planes and I'm studying what happens when you look at the intersection. When you look at the intersection of them, right? What happens, how do you look at the intersection of 2 planes? Well, that's where both equations hold true, right? And so I basically derive the symmetric equations of the plane from taking two of the two planes which are intersecting and studying their how you put the equations together. When you do that, you end up finding the components of the cross product as the directions. Now, if you think about that, that makes total sense, because if you've got 2 planes intersecting, right? If 2 planes intersect, that means that the line of their intersection is tangent to both planes. But the tangent to both planes then must be perpendicular to the normal of both planes. What vector is perpendicular to both normals? The cross product of the normals. So if you have 2 planes and you want to find their line of intersection, what you do is you take the cross product of their normals. That points in the direction of the line of their intersection. That's what I'm deriving here. This is in some sense a derivation of the cross product, but whatever. Here's a picture of what I was just talking about. Not especially important. The other thing I should talk about is what's a graph? Well, a graph is when we can write z as a function of x and y, or in principle if we could write y as a function of x and z, or in principle if we could write x as a function of y and z. If you can write if you can express your surface such that one of the Cartesian variables is a function of the remaining two, this is called a graph, right? You guys know about graphs, y equals f of x, that's a graph. Well, this idea persists into 3 dimensions. It's just, more annoying. Now, typical calculus books spend the lion's share of their effort on z equals f of x, y. That's like pretty much the whole universe of discussion half the time. But unfortunately, that's kind of nearsighted. All right. We can skip past this. These are kind of more advanced things. There's some homework problems that are based on this, or a problem. There I'm describing basically how to project things onto a plane, Anyway, we can talk more about these some other time if there's a question. Here I'm actually showing, this actually proves that here I'm explaining why the projection gives you the closest point to the plane in this context. Like the proof is essentially down here. This distance is smallest when that piece is 0. But that piece is the part which is not from the projection, essentially. That's the orth. Anyway, all right. Let me get to the point here. So additional examples. Read through here. There's like tons of like mix and match kind of things. Like, well, simple enough. Here, let L be aligned with direction vector this, point that, find the vector and scalar parametric equation. I think all you guys will be able to do this one. Like that's not. No one's gonna get stuck on that homework problem likely, right? Let's see. I do have some trickier things though. Well, this one's not that tricky either, is it? Here's a line. There's the parametric equations. Find the direction vector and the natural base point. So how to do that? I just undo the equation. Point plus t times vector. That's the base point. That's the direction vector. Right? Doesn't have to be tricky. I must have a tricky problem in here somewhere. Suppose L1 is a line with that formula. L2 is a second line with that formula. What can we say about L1 and L2? Well, that's a vague question, isn't it? So what would you do when you're faced with a question like this? What are the things that we can talk about in a line? The base point, right? The direction vector. So that's the thing that jumps out to me. Try to compare them. Is there anything to compare? Oh, well, apparently they both have direction vector in the direction 1, 1, 1, right? The one has 1, 1, 1. The other one has 3, 3, 3, right? So they're in the same, their direction vectors are parallel, right? One is a scalar multiple of the other. That means essentially they're going in the same direction. The one that's got 3, 3, 3, as we'll learn like next week, that means that that path is going faster. Because the direction vector in this context is actually the velocity. So it's got a larger velocity. The magnitude of the velocity, which is the speed, is faster. In this case, 3 times faster. Let's see here. Now here I've asked for a parameterization of a line which goes through that point and is parallel to the line through this and that, right? So basically you can just take the directed line segment from those 2 points. That gives you the direction vector and use the point which is given as a base point. Well, I'll accept it. There are more curses. That double scrolling in here, it drives me nuts. Where was I? Ay. Well, we'll come back and talk about collision versus intersection in future lectures. That's not really for today. Oh, perfect. This is the one I was looking for. So you've got 3 points, PQR. Here I'm asked to do what? I'm asked to find a parameterization of the plane, a normal to the plane, and its Cartesian equation. So here we get to see for a single plane both a parameterization of the plane and also an equation for the plane. So the 2 different viewpoints you can contrast. All right? So the parameterization is really easy. You can use the trick I wrote down last time, right? This formula. P plus S times Q minus P plus T times R minus P. This is the parameterization of a plane that has those 3 points. And once you have that, you can rewrite it like this. And there you go. That's the parameterization of the plane. Simple as that. Now, when you have a parameterization for the plane, these 2 vectors that appear next to S and T are tangent to the plane. They lie along the surface of the plane. As you trace from, S and T both equal to 0 to, say, S equals to 1, T equals to 0, you're going along that vector in the surface, right? And as you go from like 1, 0 to 1, 1, anyway, as you trace through the appropriate ranges of S and T, you're going to see these vectors be basically drawn along the surface, all right? These vectors are tangent to the plane we're talking about here. So if I want to find the normal to the plane, I could do what? I could take their cross product to find the normal, right? I wonder if I did that here, though. What did I do? Let's find out. Oh, I did that. That's so boring. So I took the cross product of them. That gives me the normal. Oh, look, I used the determinant mnemonic. How quaint. And there it be. Let's check me. Is this cross product perpendicular to A and B? 14 times 1 minus 14 times 3. Uh-oh. Oh, yeah, 14 minus 12 minus 2. That's good, right? 0, yeah. And how about the other one? 28 minus 16 minus 8. Or did I do that right? Oh, minus 12, right? 16 plus 12 is 28. 28 minus 28, 0. Yay. Okay, good. So that's a normal to the plane. And so the Cartesian equation of the plane is that right there. There is another way you could have found the way that, what's your name? Emily would not have found the equation for the plane this way. She is a lover of algebra. You would have written x as a function of S and t, y as a function of S and t, z as a function of S and t. You would have then taken those 3 equations and eliminated S and t as to find the Cartesian equations, yes? It's in your heart. I know it. I can sense it from your previous work. And I've done that too. Like you can just write down x equals to, if we go back to here, the parametric equations for this plane, right? They'd be too close to it. Where am I? Golly, it's the wrong example. Curse you, computer. I'm not cursing people. You're allowed to curse computers, right? Is it generic curse a curse? I don't know. I hope not, otherwise I'm in trouble. Let's see here. X equals to 2 plus S plus 2t. Y is equal to what? 1 plus 3s plus 6t. Z is equal to S plus 6t, right? There you go. Those are the parametric equations for the plane. 4t. See, if you took those, you got 3 equations and how many unknowns? Let's see here. I would say 5 unknowns. Because you've got, well, how many variables? Let me say it a different way. How many variables do you got? I think we can all agree you got 5 variables, right? So in some sense, you can look at it this way. It's a problem in 5 dimensions, and you got 3 equations. So what are you left with? 5 minus 3, 2, a 2-dimensional object. But anyway, the point is you could do algebra and just eliminate S and T. But man, it's so much easier to take the cross product of the vectors to find the normal. When you know geometry, it will beat algebra usually. All right? It's how it is. So moving on here, I have additional problems about lines and planes, and we'll explore it more in the homework. Curves you already talked a lot about in Calculus 2, so I'm not going to belabor that today. Basically, here's some pictures of them. I want to find some three-dimensional. So in 3 dimensions, you can have all kinds of snazzy things like, here's an ellipse on a plane or a spiral on a plane. If you kind of feed the ellipse equation or the spiral equation you saw in Calculus 2, if you feed that into the parameterization of a plane, that will then give you an ellipse or a spiral on a plane possibly. Assuming that your plane parameterization is not wonky. Don't ask me to define wonky. Anyway, here's a picture of a helix. Here's a picture of a twisted. Listen, we're going to be studying three-dimensional curves. My point to you is if I give you x, y, and z as a function of t, you're tracing out some one-dimensional object in 3 dimensions, all right? And we'd like to understand how to categorize the shapes of these things, find their tangent vectors, all that jazz. And we'll do that next week, all right? I don't think you have any homework on that, right? Surfaces can be interesting, right? So here's z equals to x times e to the minus x squared minus y squared. It looks kind of like this thing. The color coding is different colors for different z values, right? So the most red is the highest, the most purple is the lowest point there, I guess if you're into skateboarding, that might look really fun. This would be kind of terrifying if you're a skateboarder, I guess. Don't go too far off the edge, right? Let's see here if I can find any other ones. Well, anyway. Now here is a parameterization of something that's not a plane, right? This is a parameterization of a portion of the sphere. But I don't think I have time today to do justice to all this, so we'll come back to this section probably Monday, all right? This actually fits nicely with the discussion of, say, spherical coordinates. We need to talk about other coordinate systems besides just Cartesian coordinates. So when we come back to that, we'll talk more about surfaces. So let me put this away. I just have one more thing to tell you today. Well, at least get our first. Well, you know what? Let me not be an idiot. Let me just give you the quiz now and let you have your time. So, unless there are any questions about the homework, we can. If you have a quick question, I can answer it. No.
Are we allowed to use the notes or textbook for the quiz?
Not usually.